Welcome back to session 3 of ViViMaT, the PhD sessions. Our second speaker today, Jagjeevan Bhamra, graduated with a Master's in Science and Chemistry from University College London. He spent a year at Northwestern University where he worked with Sir Fraser Stoddart investigating molecular recognition. In 2019, he joined the tribology group at Imperial College London under the supervision of Daniela Dini and James Ewan, two friends of mine, studying chemical and physical interactions between engineered surfaces and lubricants. I'm looking forward to his talk that will employ reactive molecular dynamics right after a message from our sponsor and one from my kids. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, Diamond Rock and Roll.
Hello everyone, my name is Jagjeevan Singh Bhamra and I'm a second year PhD student in the tribology group at Imperial College London. Today I'm going to be discussing how interfacial bonding and mechanochemistry controls the friction in diamond rock contacts. Our purpose statement for this project is essentially trying to understand how polycrystalline diamond composite materials interact with rock surfaces. Rocks generally have very heterogeneous surface chemistry, and in this study we use alpha quartz and calcite to represent granite and limestone respectively. For this study we use non-equilibrium molecular dynamics, NEMD, a bond order-based force field, REXFF. Again, I'll go through both NEMD and REXFF in the next few slides. Just to know, all simulations were performed using the open source software LAMPS, and visualization was done using Ovito. This slide is just to show the different simulation scales used in the modeling of tribological systems. At the moment, and for this study, we are focused around the middle of this schematic, looking around classical MD, which aims to model on the nanopicosecond timescales and angstrom length scales. On one extreme, we can see ab initio MD and DFT, which aims to look at systems on a much smaller timescale and a smaller length scale. On the other extreme, we can see continuum models, which look to examine general behavior of systems on a much larger scale. There are also multi-scale and multi-physical approaches that are able to combine these time and length scales, which could be fundamental in understanding unsolved issues in the field of tribology. NEMD is mainly used to understand the fundamentals of fluid flow by driving a system away from equilibrium. There are plenty of ways to achieve this. We can use temperature or pressure gradients, stress gradients through an expansion and contraction system. We can play around with diffusion coefficients, for example, applying a charge to certain atom types which creates charge imbalances in the system, and then we can examine how the system behaves. This schematic illustrates how wall motion is used to create a non-equilibrium state. A normal force is applied to the top wall, and both walls are moved in opposite directions. Here we can only see the tip moving, but generally both walls are moving. After a system reaches non-equilibrium state, we analyze its behavior by measuring the steady state response. And because wall motion is most relevant to tribology, we'll be using it to examine the NEMD behavior of diamond quartz and diamond calcite. REXFF was developed by Adrie van Duyn at Caltech in 2001, mainly because density functional theory was so impractical for large systems. With DFT, there is a large computational cost associated, and you cannot use it to study dynamic evolution of a system like we want to do with NEMD. REXFF is an empirical method where DFT calculations are used to train parameter sets which can then be used to model chemical behavior. We can examine bonds breaking and forming, which is unlike traditional force fields where bonds can only twist and stretch but are never broken or formed. This figure here shows the development of REXFF and how widely it has become. It was originally developed for carbon, hydrogen and oxygen systems only, but now there is huge availability. Also, REXFF is broken down into 3 main branches: a combustion branch, an independent branch, and an aqueous branch. The branches show the parameter sets available for a wide range of systems. However, you cannot combine these sets from different branches without extensive reparameterization. The good thing about REXFF is that it's continually being developed and updated. I'm going to quickly go over mechanochemistry because it's quite fundamental in what we're doing here. Mechanochemical reactions are quite different from chemical reactions that occur upon heating, photoirradiation, or electrical bias. Instead, we apply a mechanical force or stress to the system. A mechanical force can lower the reaction energy and push the system through a different reaction pathway. Here we can see two different reaction pathways. The dotted line is where the mechanical force has been applied to the system, and the system then goes through a lower energy transition state. The mechanical stress is essentially acting as a catalyst for these types of reactions, which may not occur under normal circumstances. Frictional heat can induce thermal reactions, which can then lead to solid surfaces wearing away or fracturing. High energy particles such as electrons and photons can be emitted through a process known as triboplasms or triboemissions. These high energy particles can then lead to electrochemical and photochemical reactions, which can then initiate and catalyze chemical reactions. A mechanically assisted thermal reaction essentially lowers the activation barrier. The reaction rate or yield can be shown in this Arrhenius type equation, which emphasizes the catalytic nature of mechanical stress. Here on the left we can see a Morse potential that describes the interatomic interactions for the potential energy of a diatomic molecule. It clearly shows that for a stretch bond, the dotted line, which is a bond that has undergone some sort of mechanical stress or force, that the dissociation energy is reduced significantly as the bond length increases when compared to an unstretched bond. Moving on, the tilted potential energy profile model shows that the structures of the reactants and transition states of a given reaction can be affected by mechanical force. This idea was first introduced by two chemists named Walter Koolman and Henry Eyring in the 1940s. This model can be understood using the schematic here on the right hand side. The solid line shows the absence of a mechanical force, and the dashed line shows the same reaction but when a force was applied. The idea behind this model is to suggest that by applying a mechanical stress, the reaction can go through a lower energy alternative pathway. The applied force tilts the reaction pathway to a lower energy, and so how the model gets its name. This is just a basic explanation of this type of chemistry. A quantitative explanation can be found in the references below. I'm going to briefly talk about the development of the REXFF models that we'll be using in the study. On the left is a comparison of the DFT and REXFF bond dissociation for two hydrogen molecules from the first REXFF model developed in 2001. On the right is a comparison of the energy relation for the oxygen-silicon-oxygen bond angles. The silicon oxide model on the right was also one of the original REXFF papers for non-carbon, non-hydrogen, and non-oxygen atoms. Both models show the accuracy of REXFF when compared to TFT. Again here we have more comparisons for the silicon-silicon-silicon bond angle and the silicon-silicon bond length. Just some more evidence of emphasizing how accurate these REXFF models are and the advantages they can bring to studying relatively large systems at reduced computational cost when compared to DFT. So instead of examining only a few molecules like we would in DFT, we can look at a few thousand and study dynamic behavior of these systems. In 2012, David Newsom then combined the two models we just discussed to develop a model that was able to describe silicon carbide materials. He combined the silicon carbon, silicon oxygen, silicon silicon, and silicon hydrogen quantum data and parameterized the model using DFT dataset describing silicon carbide crystals. The figures here compare the REXFF results from the silicon carbide equation state and for an oxygen atom binding at different positions on the silicon carbide crystals. We can see that the energy of the crystal structure and the binding energies are in good agreement with DFT calculations, and they also match very nicely with experimental values. Because the quantum mechanics training set used to develop this model contained all the data for silicon oxide, silicon, and carbon, hydrogen, oxygen, this model can also represent silicon oxides, diamond, and graphite, and therefore why we chose this model for the quartz system. The calcite force field that we use in the study is still currently in development, but here are two schematics showing its accuracy. We can see good agreement between the REXFF and DFT energies for the calcium-oxygen-carbon angle and the calcium-carbon off-diagonal. The energy differences between the two models are comparable to the typical error of DFT calculations. The training set also included condensed phase data for the equational state for the condensed phase of calcite. The REXFF model was able to reproduce the equilibrium density of calcite from DFT within the uncertainty of the measurements. It does, however, slightly underestimate the volume energy curvature when close to the equilibrium density. On the right-hand side, we can see that the vibrational frequencies of calcite calculated from DFT and REXFF are in good agreement. Initially, we examined the variations in friction force with normal force using macroscale tribometer experiments, with the black line showing diamond on granite and the red line showing diamond on limestone in a humid air environment. In both cases, consistent with Monton's friction law, the friction force increases approximately linearly with normal force. In an aqueous environment, we see the same trend, that the friction coefficient for diamond on limestone is significantly higher than for diamond on granite, but only more exaggerated. It was noted with the experiments that the limestone powder strongly adheres to the diamond tip, which has previously been shown for polydiamond crystallite materials on carbonate materials. Here we can see the simulation results for a diamond asperity sliding over a calcite and quartz surface. Like the experiments, the steady-state friction force increases linearly with normal force for all steady systems. For the dry case, the schematic we can see here, the trend was reversed, and the friction coefficient was higher for diamond on quartz than for diamond on calcite. Just to re-emphasize the point, we use calcite to represent limestone and quartz to represent granite. Unlike with the dry case, when a water monolayer of 50 water molecules was added between the tip and the substrate, so the figure on the left-hand side, the friction force or friction coefficient for diamond on quartz decreases significantly and the friction coefficient for diamond on calcite increases. When 150 water molecules were introduced to the system, so the figure on the right-hand side, this trend, like we saw in the experimental results, was exaggerated and the friction coefficient for quartz decreased further and for diamond on calcite increased. We monitor the indentation depths with sliding time to estimate the ploughing contribution to friction. During the sliding phase of the simulation, the tips indent into and plough through the substrates. In all cases, the indentation depth is deeper for calcite than it is for quartz. This is expected since the quartz has significantly higher hardness than calcite. We assume that the indentation depths are not going to impact the relative friction between diamond on quartz and diamond on calcite. This is because if we assume isotropic hardness, the tip will indent less into the quartz substrate, but it will also experience great resistance to sliding at a given ploughing depth. Here, for the dry case, we can see how the interfacial bonding increases with sliding time, reaching a steady state around 500 picoseconds. More interfacial bonds are formed, and the rate of their formation increases as the load is increased. This suggests that the interfacial bond formation is a stress-assisted thermally activated process or a mechanochemical process. In a stress-assisted thermally activated process, the activation energy, which determines the rates and reaction pathways, is reduced by the application of stress. The black dotted lines show the initial rate fittings to the Arrhenius equation we saw previously. Here we can see the same procedure as before. Note that with the introduction of water, less interfacial bonds form for diamond on quartz than for diamond on calcite. Again, I'm just emphasizing the accuracy of our fits and in estimating reaction rates for these interfacial bond formations. The stress dependence of the rate of interfacial bond formation can be used to determine the activation volume. Here we can see how the rate of interfacial bond formation varies with applied pressure. The rates were calculated from the fits from the previous slides. Like many stress-assisted thermally activated processes, the rate of interfacial bond formation increases exponentially with applied pressure. In Figure A, with no water molecules present, the rate of interfacial bond formation is higher for diamond on quartz than for diamond on calcite. The slopes of the linear increase of the natural logarithm of the rate against the applied pressure determines an activation volume, which is higher for diamond on quartz than for diamond on calcite. The rates and activation volumes are similar when 50 water molecules are added, like we see in Figure B. I just want to emphasize that in this case, the friction coefficients were most similar during this environment. Figure C shows the 150 water molecule system and the rate of interfacial bond formation is higher for diamond on calcite than for diamond on quartz. So essentially the trend is reversing as more water molecules are being added to the system. Here we can see the steady state number of interfacial bonds for the dry systems. We observe only one main interfacial bond, which is between the diamond tip and an oxygen atom in either the quartz or calcite substrate. There is negligible bonding between the tip and silicon in quartz or calcium and carbon in calcite. We can see a greater number of interfacial bonds for diamond on quartz, which results in the higher friction we saw previously. When water is introduced to these systems, we observe different types of interfacial bonds forming. For both cases, we observe bridging bonds as a result of water molecules degrading. For calcite, there are diamond atoms bonding to a calcium through a bridging water-oxygen atom and to an oxygen via a water-hydrogen atom. There are also direct diamond-oxygen bonds like we saw in the dry case. The same is true for diamond and quartz, except there is a diamond-oxygen-silicon bridge bond instead of a diamond-oxygen-calcium bridge bond. We can see that the total number of interfacial bonds increases for calcite and decreases for quartz when water is added to these systems. Mainly, there seems to be a high affinity for bridging bonds to form in the calcite system and a reduced affinity for diamond directly bonding with oxygen in the quartz systems. The inlets are color-coordinated snapshots of these bonds in the respective systems. Here again, I just wanted to show that the trend is more obvious when the number of water molecules present has increased. We see further decrease in the number of interfacial bonds for diamond on quartz and a slight increase in the number of interfacial bonds for diamond on calcite. Finally, to further emphasize that friction is governed by interfacial bonding, we can see here that the mean number of interfacial bonds formed was correlated with the mean friction force for the different systems and conditions that we studied. For the water-present systems, the mean friction force increases approximately linearly with the mean number of interfacial bonds for both diamond on calcite, which is on the left-hand side, and for diamond on quartz, which is on the right. The gradient is steeper for diamond on calcite and therefore implies that the interfacial bonding in diamond on calcite is stronger and requires more energy to break than in the diamond on quartz systems. I'd like to thank Daniele and James for all their help and guidance and their supervision. I'd like to thank Carlos for his help with the REXFF data analysis. I'd also like to thank Adri and the banker for the REXFF force field development. Finally, I'd like to acknowledge Baker Hughes for providing me with PhD support and to both Mark and John for all their help and guidance. Thank you very much. Thank you all for listening to my presentation. Please feel free to ask any questions through the appropriate channels or emailing me at the email address here below. Thank you again.